International law says that carbon dioxide emissions should be reduced to zero and suggests that global warming should be kept to 2 degrees. What does a cost-benefit analysis have to say about these matters? In a cost-benefit analysis, you maximize your net benefits. Let's call them W, and they are a function of your emission reduction effort, E. So this is what we want to maximize. Your net benefits are defined as your gross benefits minus the costs, and both are a function of your emission reduction effort, E. Now, if you want to maximize this, then we write down the first order conditions for optimality, and that is that the first partial derivative of what you care about, that's your W, over what you control, that's your E, so dW dE must equal 0. dW dE is equal to the marginal benefit minus the marginal cost should equal 0. And then we have our equimarginal principle that the marginal benefits should equal the marginal costs. The marginal benefits of our action should equal the marginal costs of our action. Now, this is if emission reduction effort is a static problem. Of course it isn't. Climate is a dynamic problem. If you have a dynamic problem, what you want to do is maximize your net present value. We still call it W, it's still a function of our emission reduction effort E, but now we have E at emission reduction at time 0, at time 1, and so on and so forth. Net present value is the sum over the net benefits. That is still benefit minus cost. The typical assumption in this kind of analysis for climate policy is that emission reduction is a flow, but climate is a stock problem. That is how we typically conceptualize this. And that means that the costs at time t are a function only of the emission reduction effort at time t, but not at what is going on in previous periods. On the other hand, the benefits of emission reduction depend on what is going on in the same period, but because CO2 accumulates in the atmosphere, it also depends on our emission reduction effort in the year before that, and so on and so forth. And then, of course, everything is discounted at the rate 1 plus r to the power t. This is your net present value. If you want to maximize this, we write down the first order conditions. Essentially, this is benefit minus cost, so we can split them. We can bring the costs already to the other side of the equation, and we can have that marginal benefits equal marginal cost. But it's a little bit different. If you take the first partial derivative of this expression here to E, then we have dC dE, just as we had before. But of course, we evaluate this at a future point in time, so we have to add the discount. We have to multiply the discount factor 1 over 1 plus r to the power t. On the benefit side, we still have the B and the E, but the benefits now are not just in the same periods, but if you reduce emissions in the year 2020, then you do not just have a benefit in the year 2020, but also in the year 2021, in the year 2022, and so on and so forth. So we start from S is 0, we have the B, the E, so this is how much benefits at a future point in time improve if we reduce emissions now. That, of course, has to be discounted with the rate 1 over 1 plus r to the power t plus s, and we split that in t and s. And then we have 1 plus r to the power t here, we have 1 plus r to the power t here. This is in the summation, but does not depend on s, so that goes in front, and then it drops out. So this is the expression that we have. And this then holds for all periods t. So what we have conceptually is that the marginal costs of emission reduction should equal the marginal benefits of emission reduction, but they are not now an instantaneous benefit, but they are a stream of marginal benefits over time that are discounted back to the period in which we reduce our emissions. So this is how you would do a cost-benefit analysis of climate policy, of optimal greenhouse gas emission reduction. And we have seen these numbers. We know the answer to this already. We talked about the marginal cost of emission reduction. That is essentially the carbon tax that you want to impose, and I showed it as a table, but here I show it as a graph. This is actually the same data, and it is essentially what you see here on the horizontal axis is the concentration of greenhouse gases in the atmosphere in the year 2100. So this is essentially, as you go further to the right, you have more stringent climate policy. And then on the horizontal axis, you have the carbon tax. You have what it would cost. And the way to read this is that you want to stabilize at 500 parts per million by volume, you need to impose a carbon tax in the year 2015 of around $110 per ton of carbon. That is one way of reading the graph. You can also read it in the opposite direction. That is, if you impose a carbon tax of $10 per ton of C, then you end up somewhere around, this must be 675 parts per million by volume. So this is the marginal cost curve, and this axis here, of course, is logarithmic. So it looks linear, but it is an exponential curve. The thick line in the middle is the median of the model results as showed before, and here you're looking at the percentiles. We also looked at the marginal benefit of greenhouse gas emission reduction, and that is the social cost of carbon. There's a slight nuance here. This is again a PDF, as I showed before, slightly different shape, doesn't really matter, but you see three alternative curves here. The social cost of carbon here means if we evaluate the marginal damage cost of climate change, if we calculate the additional damage that is done if we emit 1 extra ton of CO2 along a path where there is no emission reduction. I call that a social cost of carbon, but you can of course also, what you should be doing is impose that as a carbon tax, and as a result emissions fall and climate change is a little bit better, and therefore your social cost of carbon falls, and that is what I call here the PQ tax. And what you see is, yeah, there is a reduction in the social cost of carbon or in the marginal damage cost, but it's not that large. So this feedback of reduced emissions if you impose a carbon tax is actually not that substantial. So now we know the answer. We know that we need to equate the marginal costs to the marginal benefits. We need to equate the marginal costs to the marginal benefits. The best guess here is around $30 per ton of carbon. So to a first approximation, the cost-benefit analysis will say, well, we're going to impose a carbon tax of $30. We're going to end up at around 625 parts per million by volume at the end of the century. That is essentially what a crude cost-benefit would tell you is the optimal climate policy. That is essentially what is in all these cost-benefit analysis of climate policy. This is essentially what they do. Typically, they write down a much more complicated model, but by and large, this is what they do. So this is a cost-benefit analysis that has a lot more bells and whistles, but essentially equates marginal cost to marginal benefits. This is done by Bill Northam, and he imposes a carbon tax now of 30. But more like 40 in the beginning, and then lets it ramp up over time. And what happens to the concentration of CO2 in the atmosphere is that the black curve here is emission is a policy, is a scenario without climate policy, and then in green you're looking at the atmospheric concentration of CO2 if there is a climate policy, and lo and behold, he ends up at around 600 parts per million. So he imposes a slightly higher carbon tax than I suggested and reaches a slightly lower concentration. Now, this was the first cost-benefit analysis that was ever done of greenhouse gas emission control. It was done by Bill Northam, who you see displayed here, and of course he won the Nobel Prize for this work. And essentially the question that he asks in these papers, and there's been a series of papers, the first one published in 1982, a famous one in 1991, and then a series of refinements later. And essentially the question that Northam asks is, if the world were ruled by a benevolent dictator, by a philosopher queen, what would she do? Now, this is a silly question to ask because the world is not ruled by a philosopher queen. On the other hand, it's a very smart question to ask because we actually cannot do better than what the philosopher queen would do. The philosopher queen maximizes net present welfare, it maximizes human well-being, and you cannot improve on this. So any policy, any more realistic policy, has to be compared against this efficient yardstick. And when Nordhaus asked this question, he found essentially three conclusions, and they are given here. And he says, well, we start with a little bit of emission reduction, we start with a gradual deviation from the no climate policy path. That deviation grows over time, climate policy accelerates, but by the end of the century, CO2 concentrations are still going up. That is essentially what Nordhaus found. And people were terribly upset with Nordhaus that this is what he recommended. So there has been, since he first published this, or rather since the 1991 paper, there have been tons of papers trying to overturn what Nordhaus concluded. So let's look at the success of these subsequent studies, or maybe the lack of success of the subsequent studies. The first part of Nordhaus's conclusion, that you want to start slow and accelerate later, is robust. It doesn't matter what you throw at the problem, you always find that it's best to start gradually. And the reason for that is that a lot of emissions are set in stone. And that is illustrated in this graph here. So a lot of things that determine our emissions are essentially long-lived capital. So a coal-fired power plant has a lifetime of 40 to 60 years. A gas-fired power plant, 25 to 40 years. A car has a lifetime of 20 years. Buildings have a lifetime of hundreds of years sometimes. And it's those sort of things that determine our emissions. What you see in this particular graph, was published in 2019, is what if we take the capital stock as it is in the year 2018 and assume that everything lives out until the end of its natural life and emits what they did on average previously. So they built a database of the age of power plants and industrial equipment and vehicles on the road and so on and so forth, and then said, well, this power plant was built in 2015, so I'm going to assume that it will live until 2055 and then retire. And this car was built in the year 2002, so I'm going to assume that it retires in the year 2022. And it's going to drive its average distance. If you do that, then this is the emissions that you would find. And this is essentially the committed emissions, and that makes a total of 850 gigatons of CO2. This is a rather large number. Just to put it in perspective, this 850 gigatons of CO2 compares to the carbon budget. If we want to limit global warming to 1.5 degrees Celsius, then we can only emit somewhere between 420 and 580 additional tons of CO2, gigatons of CO2. We're going to blow that budget just by having capital live until the end of its natural life. If we want to limit the temperature to 2 degrees, then we have a little bit more room. We can emit at another 1,200 or perhaps 1,500 gigatons of CO2, but most of that will be blown by existing infrastructure. If you start adding the infrastructure that is in the planning stage or is currently being built, then of course you have to add almost 200 to this. Now, the implication of this is that if you want to cut emissions really, really deep, then you have to prematurely retire capital. It's relatively cheap to replace stuff if it has reached the end of its useful life. But if you're going to take a brand new power plant and you're going to just mothball it or take it down again, that is very, very costly because it hasn't had time to earn back the capital that was invested in it. So rapidly reducing emissions essentially means prematurely retiring your capital. It means tearing down your buildings. It means doing away with perfectly good vehicles. It means taking down perfectly fine power plants. So this is the graph. If you look at sort of what sort of activity, and here we see what it is by country. So it's not just that we need to convince ourselves to tear down our houses and build new ones. No, we actually need to convince the Chinese and the Indians and the Brazilians to do this. So for that reason, because so much of our emissions is set by the capital stock that turns over very slowly, you always want to start. Slow. How fast you want to accelerate after that is very sensitive to assumptions. You can essentially, some studies say, well, climate policy should intensify at a rate of 1% per year. Other studies say it's 5% per year. It's somewhere in between that is a reasonable range. There are even studies that say you should decelerate. You start with a big bang and then decelerate, but that only holds if in the very first period you solve the climate problem. Then after you solve the climate problem, you can de-intensify, you can extensify your climate policy. But until that point, every study says you should start slow and accelerate. It's just that the rate of acceleration is not known with any sort of precision. But basically everybody says you should start slow and accelerate. The final part of Nordhaus's conclusion, and that is the one that got people so very, very upset, that you should never stabilize concentrations of CO2 in the atmosphere, that is robust. And that is the thing where people threw the kitchen sink at the poor man, but nobody has been able to overturn this particular conclusion. And this follows from the structure of a cost-benefit analysis. So what I said is that in cost-benefit analysis, you want to equate the marginal cost to the marginal benefits, which would sort of get your marginal net benefits to zero. So this is the marginal benefit curve. This is your marginal cost curve. And then the cost-benefit analysis says these two should be equal because that maximizes your net benefits. So that is what a cost-benefit analysis says. So the question is, are these curves credible that I showed here? So this point here is where there is no emission control. This is essentially the point where your emissions would be if there was no climate policy. And the reason that it is like that, because essentially if you go beyond this point, then you're hurting yourself. So this is the point where you've heated your house and it's nice and comfortable, and yes, you can heat your house more, but it does not bring you any benefit because it's warm enough, and it actually does cost money to heat your home, so you would not go there. Or this is the point where you've reached your destination, and yes, you can go around the block one more time, but that would mean you're paying in fuel and you're losing time, so why would you do that? This is just the point at which you stop burning fossil fuels. That is this point. And then emission reduction pushes you away from the unregulated emissions towards, and this is the point where the environmentalists say we should go towards zero. And the first bit of emission reduction is cheap. We talked about how a lot of energy is wasted, and that means you can reduce it on the cheap. We also talked about that by now wind and solar are near competitive. Maybe they are competitive with fossil fuels in power generation. And that means you can reduce emissions from the power sector at a low cost. But then we talked also about reducing emissions in the transport sector, and there are no good solutions yet. They may be there in 5 years' time or maybe in 20 years' time, but there are no good solutions yet, and that means that it's relatively costly to reduce emissions. So this curve goes up. And then, of course, here we have those things. The good thing about transport, we know the technical solution. It's expensive, but there's also sources of greenhouse gas emissions, and we actually don't have a good solution yet to reduce those emissions, and that would be methane from rice paddy, for instance. I'm actually not quite sure how to do it, or for that matter, the emissions from space flight, where we actually don't know how to solve this. We don't know how to get satellites up in the sky without emitting CO2. And you may say, well, I don't care about satellites. To which I would answer, well, that is actually what keeps your mobile phone going, and then you may counter, well, but there's plenty of satellites up there already, which is true at the moment, but a satellite has a lifetime of around 10 years, so you need to replace them, or you need to give up all your mobile communication. So, and we don't know how to do this. So, yes, these costs go up and up and up and up. Now, what does the benefit curve look like? Well, here, the benefits of emission reduction are large. Say the world were to warm by 7 degrees if you don't cut emissions. And then if you start cutting emissions, you essentially bring warming down from 7 degrees, which many people would say is catastrophic, to 6 degrees, which many people would say is pretty bad, but not as bad as 7 degrees. So initially your benefits of emission reduction are high. But then we're not cutting emissions, we're not cutting global warming from 6 to 7 degrees, but from 5 to 4 degrees, and from 4 to 3 degrees, and from 3 to 2 degrees. And then it's harder to argue that this would bring enormous benefits. It would still bring benefits, but perhaps they're smaller. That is not what we're saying. Here you're cutting climate change from 1 degree to half a degree, from half a degree to 0.1 degree, or from 0.1 degree to 0.01 degree, and actually stopping climate change. And then you can no longer argue that that would have a large benefit. It would be very costly because you have to go reduce emissions that you don't really have a proper alternative for. It would be very costly, but going after the last bit of emissions would bring very little benefits. And for those reasons, a cost-benefit analysis almost always finds an interior solution. It is never optimal, almost never optimal not to cut emissions, but it's also almost never optimal to cut emissions to zero. And that is why, however you phrase your cost-benefit analysis, you're always going to find that it is not enough to stabilize concentrations. So, as I said, there have been many challenges to Nordhaus's 1991 paper, but nobody has been able to overturn this conclusion. And there's one exception to this, and that is if you introduce a carbon-free backstop. If you have a carbon-free backstop in your model, then you would stabilize CO2 concentrations in the atmosphere. So what is a carbon-free backstop? Well, a carbon-free backstop is a source of energy that does not emit carbon dioxide. This is not a crazy assumption because we know these things are out there. A carbon-free backstop is also something that outcompetes fossil energy at a particular carbon tax, a finite carbon tax. Again, this is not a crazy assumption to make because we know that these things exist. It depends what that carbon tax should be, whether you're looking at power generation or aviation, but there is always a carbon tax at which the alternative, a carbon-free alternative, becomes available and competitive. Carbon backstop also doesn't just need to compete with fossil energy at the margin, but it actually needs to take over the supply. It actually needs to supply 100% of the energy needs. And essentially the technical assumption here is that there's an abundant supply that is available at a constant cost. And this is a peculiar assumption. At the moment, if you put wind turbines in the windiest places and near population centers, then wind competes with coal-fired electricity and gas-fired electricity. That is true at the margin. But if you want to replace all coal-fired and all gas-fired electricity, then you need to put wind turbines also in places that are further from population centers, from demand centers, and that means that you have higher transmission costs. And you need to start putting wind turbines in places where the winds are weaker, and therefore your costs are higher. So this is a strong assumption. Ditto for transport. Electric vehicles are great second cars. If you have a car, a petrol car and an electric car, then for most things you would use your electric car, but for long distance driving, electric vehicles are perhaps not so good. So you can replace a lot of activity, a lot of driving with electric vehicles, but at the moment you can't replace all driving with electric vehicles. And if you were to do so, you would actually suffer a substantial welfare loss for the sort of 10% of journeys where electric vehicles are simply no good at the moment. So this assumption is a strong assumption and not a particularly credible assumption. Furthermore, you need to assume that the backstop continues to dominate the energy market forever, until eternity. And of course, if this carbon-free backstop takes over, then your CO2 emissions go to zero, the climate policy disappears, so there is no longer any need for a carbon tax. But you never go back to emitting CO2. You never go back to fossil fuels, even though there's still a lot of fossil fuels in the ground. We know that it's there, we know how to get it out, we know that we can burn it and make electricity or do other things with it, but we are never tempted to go back. And this is a very strong assumption. It's hard to imagine that this would ever be the case, because don't forget that the Saudis are pumping oil at $5 a barrel. Yes, it may be that at one point biofuels take over. If you have a carbon tax of $100 or something, then biofuels outcompete Saudi oil. But it's very hard to imagine that biofuels will always compete with that very cheap oil that is still in the ground. But if you are prepared to make these assumptions, then at a certain carbon tax, the economy will decarbonize and will never look back. And that means that you stabilize concentrations at a particular point in time. If you're prepared to make the assumption of a carbon-free backstop, then yes, a cost-benefit analysis would justify emission stabilization, otherwise it would not. Now, this is true if there's a single social planner that rules the entire planet, your benevolent philosopher queen. Steven will talk about what happens if there are many countries, and the implication of that is if you have many social planners who interact, then things only get worse. Emission reduction falls, emissions go up, but that is for later.